Welcome. In this week, we are going to start with one of these most interesting aspects, and that's about video analysis. Now, till whatever we have done on the lectures as of now, they were to do only with 2D images or single frames over there, and it was frozen over time. So, you don't have this time varying nature of these images or anything created out over there. Whereas, one of the major chunks of analysis which we end up doing for current applications are all on videos, and what comes down is that while you can always treat down videos as just a bunch of frames over there and then keep on operating one frame at a time and still get down your results coming out of it and use them for your further analysis or summarization of whatever analysis you want to do, the main point or the main aspect which we often tend to forget is that there is some sort of a temporal consistency between these frames as they keep on coming. And what that necessarily means is that we should be in some way able to use the features which come down on the feature space over here in terms of just the spatial dimensions. Now, do they have some sort of a cross dependent relation between the between time frames? Now, nonetheless, what should also be another interesting meaningful thing over here is that since we have these videos available which can otherwise be just considered as a chunk of frames, then we should also be in a position somehow to run down some sort of convolutions over there. Now, whatever convolutions you were doing till now, they were all spatial. So, there was obviously a 3-dimensional array, but then the third dimension was just the number of channels which comes down, and as far as till we have been concerning over here in terms of these tensors. So, the way these are represented is that the first dimension is actually the batch size, the second dimension is where you have the number of channels, input channels over there, the third dimension is the x axis, and the fourth dimension is the y axis present over here. Now, if I am considering something in terms of video, I need to have this extra dimension over there which is of time. So, what we do is while typically video files as such are recorded in a way where you have the time axis as something which supersedes the color axis over there, which means that in our representation it should have been batch dimension, then the next dimension is what represents the time, the next dimension is what represents the color channels, and then you have x and y. But then we don't do it for a very specific and obvious reason over there, because over color channels you cannot convolve anything. So, you need to convolve it over the time dimension over there. So, how it works out is what I am going to do. So, it's really hard to just keep on explaining in terms of speaking out over here. So, I will just be using a few of these illustrations to get this concept clear. So, today we will be doing about understanding the very basic concepts of how to handle down videos, and can I get down something on the spatial side of it to work out on my videos. In the next lecture, I am going to get you introduced to a sequence modeling concept called as recurrent neural network, which is something which we use for as such is typically being used for speech and natural language processing or any kind of a sequence data analytics. And then how do we end up treating these say image frames over here on a video volume in terms of and then extracting some features which can now be fed down to my recurrent neural network for sequence modeling. So, this is what how the flow will be going down, and then subsequently the next day we will be looking down into how to engage say a spatial convolutional network plus a temporal learning network with respect of a recurrent neural network together in order to get some sort of an analytics done over a whole video volume. So, let us get into the organization over here. So, how it is done is today I am going to rebrief you this sort of a similarity between images and videos. So, we have already done the images part of it when we were looking into the early courses, early lectures in this particular course in the first week itself, and then how do we deal with images, and then in terms of convolutions what happens over there. Now, today I am going to extend that whole concept over to videos, how it goes down. And then I will enter into the data organization and video tensor representation. So, this is what I was telling you initially just a couple of minutes ago, that what dimension of my tensor is going to represent which aspect of the data. Subsequent to that, I will be getting you introduced to neural networks for video handling, and this will be very specifically just convolutional neural network, because as such if you have a fully connected network over there, then it becomes easy because you can just stack down all your neurons over there irrespective of whatever you are doing, and then it can directly be used. But the moment you are speaking about in terms of convolutions, then it does not become so easy. So, here comes in a trick, like what axis do you convolve around for each of them, and what happens to the number of channels, because now your data technically becomes a 4D data if you have a color video representation. So that's what we will be doing down in this neural networks for video handling, and then enter into convolutions on video tensors, and what is the input and output size relationships between each of them, and take in a critical case, a very typical case, and see down what is the criticality of handling down direct temporal convolutions, spatiotemporal convolutions on these kind of data. And then enter down into challenges, and following that I will give you a very brief introduction to spatiotemporal modeling for deep learning, and where it actually comes down on the spatiotemporal concepts over there. Okay, so as far as images and videos are concerned, so typically if you look down on our earlier notions, then this was an RGB image given down. So R, G and B were the 3 different channels on the input. Now with whatever we have done till now, one thing which goes down clear to your mind is that number of channels is quite an independent aspect, and it's just dependent on the operators. And what happens down with the number of channels is that you can keep on changing the number of convolution kernels which would come down over there, and that's something which is going to play around with the total number of channels. And as a result, what would come down is that your it's not necessary that you just need R, G and B channels over here. So you can have 1 channel data, you can have 2 input channels, or say subsequently down the line as you traverse across the depth of a convolutional neural network, you have even more and more number of channels. So there are 16 channels, there are 6 channels, there are 32, 64, and this is a very generic concept. So while in the earlier days it was really quite an effort for you to understand channels in terms of what happens when they are just increasing more than 3 over there, but now all of us are sort of used to this concept. So I am just going to refer down to color images with a simple example of a 3 channel thing, because it makes it easier and intuitive to do. But later on, all of these are generically scalable concepts. So down the whole pipeline of a temporal video tensor, you have everything going down in the same way. So now if this has m and n number of columns and rows over here, so technically the size of it is represented as 3 cross m cross n, and that's for an RGB. So if your number of channels is C, then you in a general case you would represent this as C cross m cross n. Okay. Now if I have my convolution, what I would have is technically 2D matrix for each of these channels, and technically that makes up like you have a 2D matrix for each channel. So the number of just 2D matrices over there will be equal to the number of channels, and then what you do is you do a dot product for each of these 2D tensors, and then you take a average over all of these tensors together, or summation over all of these tensors together, and that's a scalar value which you get down. And this scalar value is what is representing one single xy location's output for a particular given. So if you have multiple number of kernels over there, so that will be the total number of channels which you are going to create down. Okay, so that's quite straightforward, that the number of channels in your convolution volume over there is also going to be the same as the number of channels in your input data over there. Okay. Now if I look down at my video side over there, so the difference what it comes down is that it's going to be a collection of frames. Okay. So over time I have my camera and I am shooting down a video. So what that means is that I am looking forward over here, and then it keeps on shooting, and then between so what I essentially get is a series of 2D frames, and each arriving with a fixed difference of time. So if I have a 50 FPS or 50 frames per second of a video acquisition system, then with a difference of 20 millisecond, I will be getting down the subsequent frames coming down to me. And what that means is that this whole tensor is now going to have a size something called as t cross 3 cross m cross n, where t is the total number of frames which I am considering along the time dimension over here. And now given this whole understanding of t cross 3 cross m cross n over here, what we do get to understand is that in terms of my technical way in which how this video is located is that I have 3 cross m cross n, this is a 3D matrix over here, and then I on my 4th axis over here, I am just going to pad it down. So for us, the priority of the axis is that the major axis is something which comes at the first point over here, at the first dimension for my data. So this is where I am going to use all of this and stack it down. So this is typically how it's represented in terms of a video tensor volume. So whenever you are trying to access a video from a video file, AVI file or something, and write it down to a MAT file or a HDF5 file, this is how it would be represented. But the problem is that this is not how the tensor gets taken care of if I am trying to do a convolution over there. So I will have to make some changes over there. Okay. So, now for organizing this data and the video tensor, this is what we typically end up doing. So, I have my video which comes down to me where the frame size is m cross n, and then I have t number of such frames, such that this is the organization of it. Now, what I would technically do is I would pull out each of these color frames separately. So, each channel is pulled out separately, and then what I end up getting is my channel is going to be my priority axis over here. So, technically I would be twiddling between these two dimensions. So, t comes in place of 3 and 3 goes in place of t. So, what that means is that I have t cross m cross n volume for my red channel, I have a t cross m cross n volume for my green channel, and a t cross m cross n volume for my blue channel, such that this is something what it would be looking down. So, instead of having a 3D matrix now at each time point, I am now going to have a 2D matrix at each time point. So, first is going to be my red channel. Okay. So, this makes it as a 3D matrix of size m cross n cross t, or t cross m cross n, anything what you want to do. Now, I will have another volume of for my green channel, and that will also be of the same size. I keep on constructing another volume for my blue channel, and that is also of the same size. Now, that I have 3 of these volumes, and if I am going to somehow concatenate them along the major axis over here. So, that would mean that I need to create one more axis of the data. So, now instead of t cross m cross n, this red channel is going to look like 1 cross t cross m cross n. This green will also be 1 cross t cross m cross n, and the blue will also be 1 cross t cross m cross n. And now, if I concatenate that along the first dimension, so that is something which is going to look like 3 cross t cross m cross n. And now, this again boils down to the same kind of a philosophy as we had for our standard 2D spatial convolutions. So, in 2D spatial convolution, what you had is the batch number, the batch size, or the whatever is the index along the batch of image frames or data coming down to you. Then the next one was your number of input channels, and then you had your first dimension and second dimension of the data. Now, for us this data is now in 3 dimensions. So, it is t cross m cross n. So, that is what I have over here. This 3 is now my channels, okay. And then if I have another part of my batch handling over here, then this preceding part of the term is what would be representing my batches, and this is what comes down in terms of my 3D volume which I have for video. So, this is a time space volume, and there are 3 channels of this time space volume. This is how you can imagine it pretty much. So, there is a red channel of my time and space volume, there is a green channel for my time and space volume, and there is a blue channel for my time and space volume, and then this together creates out the whole gamut of my video, which is represented in terms of a tensor. Now, let us get into what will happen when I am trying to use a convolutional network for handling out this kind of a video. So, I will be having these kind of volumes available to me. I have my red channels volume, I have my green channel volume, I have my blue channel volume. Now, if I would like to convolve it over there, then I would need another set of kernel. Okay. Now, as a result of this convolution, I am going to get down one block volume coming down. So, essentially what it means is that this small red volume cube, which is my kernel for convolution, this does a convolution over. So, it does a dot product wherever it sits down on the first valid location over there. So, it sits at this location, it does a dot product, the green one sits over here, does a dot product, the blue one sits over here, does a dot product, and then it sums up. So, in case of your 2D convolutions, what you are imagining as a 2D matrix which sits on top of the image, one of these channels of the image, and does a dot product. The second 2D matrix for the next channel sits on top of the next channel over there for video or for your image, and then does a dot product, and the third one sits over there, and together you take it out. So, now you have to imagine the same thing, and instead of a 2D, it is now a 3D which is fitting on top of it, and this is generalizable. So, if I have some 4D matrix which is taken over n number of channels, then I can still have the same thing. That makes it hard to imagine on the first slot, but typically that is how it is going to be, and it is a generically scalable up concept. Now, my output is going to be as such just one single channel, and this will still be a time space volume based on if I had a 2D space over there, and if I am convolving, my resultant is a 2D thing. Okay. Now, if I have a 3D thing and I am convolving in 3D, then my resultant is also supposed to be a 3D. So, my convolution is 3D convolution, that is not a 2D convolution as we had in the earlier case. So, here we are just going to treat all of these convolutions as typical 3D convolutions. Now, from there, if I have another kernel over here, then that is going to lead to another channel formation. Similarly, if I have another kernel, I get down another channel which is formed, and another kernel which will get me another channel formed down. So, this also goes in line with our original understanding and philosophy, which is that the total number of channels on my output of my convolution is going to be dependent on the total number of convolution kernels I have in a particular given convolutional layer over there. So, here since I have 4 different convolution kernels, so it is going to lead down to 4 different channels coming down over here, and that is pretty straightforward. Now, there is not much to get confused in any way. Okay. Now, where comes in the interesting aspect is that you can technically see that I have increased one extra dimension of the data, and associated with this one extra dimension of the data comes in its own computational complications as well. Okay. So, let us look into one of these examples. Let us take one of these kernels over here and try to convolve it with this whole time space video volume over here, and then come down as what comes on my output, and then see what is the net effect of this output as it comes down through this kind of a convolutional concept. And let's look into the width, height, depth, and these calculations coming down. So, what is the resultant aspect of the convolution? Now, as goes down over here, so I have my time space volume, and then the 3 channels of my time space volume available. I take down my first convolution kernel, which is also a 3 channeled convolution kernel over here, and then I get my resultant in terms of a time space volume for one single channel. Okay. Now, taking down the same kind of analysis which we had done earlier. So, in your earlier analysis, what you had was that your output over here is going to be m minus w plus 2 p w divided by s w, where your O w is basically width of the output. So, you consider any one of these axes over here as your current width. So, I am taking this as my current width. I can also be putting down the same equation to do it along this any one of them. So, that is just which particular axis you are looking at. You need to understand the padding and the stride along that particular axis. Okay. Now, w is basically width of the kernel along that axis. So, if I am looking at the x axis over here, then I would be looking at what is my width of the kernel along the x axis. Then I will have my padding over there. So, I can pad down along each of these axes in a different way. So, since it is a 3D tensor over here, so in case of your 2D convolutions, you could see that you had to give down only 2 different padding criteria over there. You could like explicitly mention down, or if you are just mentioning only one padding criteria, then that is what is reflected across all the dimensions over there. Otherwise, if you are giving it within a tensor tuple, then the first one is for the first dimension, the second is for the second dimension. That's how you could do. So, here if you are giving it down in terms of a tensor tuple, then you have to have a 3x1 size tensor and not a 2x1 size tensor as you had in the spatial convolution side. So, that is the next difference which comes down over here. Okay. Now, with that you can also specify your stride, and as we had seen that you can have stride along each directions in a different way, or you can put down isotropic strides. And typically, if I am not mentioning stride in any way or padding in any way, so if there is no padding mentioned, then it is a 0, there is no 0 padding added down. So, there are no extra pads coming down. If my SW is also explicitly not mentioned, then it is just something which happens with a stride of 1, and this is what my output comes out. Okay. Now, where the challenge comes is quite straightforward. So, if I am trying to do this convolution over here with one of these blocks, and then I get down my output. Now, as I get this output coming down over here, what would happen is that this is my relationship which I had learned down. Okay. Now, let us take a very typical case, and this typical case is where my m is 224. So, my ImageNet sized frames which I was taking till now, they were all 224 cross 224 size frame. So, there were 3 number of channels. So, 3 cross 224 cross 224. Okay. Now, if I am taking say a video which is shot on the same resolution as an ImageNet over there. Okay. So, in that case I can have some fixed number of frames over there, but let us look into one of these axes as of now. Okay. So, if m is something like 224 cross 224, and this time has some other dimension, I will come down to that shortly, and say this w over here, this width is something of the size of 3. My Pw is 0 and Sw is 1. In that case, my Ow actually comes down to be 222. That is pretty simple. So, I have 224 minus 3 plus 0 divided by 1. So, that is 221 plus 1, which makes it 222. So, that is my output width over here. So, my output width is directly related. Now, that is straightforward. However, I have my time dimension. So, now I need to get down into what will happen on the 3D case. Now, say my input over here is 3 cross 100 cross 224 cross 224, which technically means that I have 100 frames available over there, each of size 224 cross 224. And now my total number of convolution channels over here I was doing it just with one channel, but my total number of convolution channels in my convolution layer is 16. So, that is the total number of kernels I have. So, now my output is going to be something like 16 cross 98. Now, where this 98 comes down is that my W over here is 3, and this is what I am going to consider isotropic across all of them if I am not explicitly specifying. So, for this axis over here, where my time axis has 100 is the size of the tensor dimension along the time axis is 100. In that case, this output along that one is going to be calculated something like 100 minus 3, because I am taking down 3 cross 3 cross 3 sized kernels. So, it is 100 minus 3 plus 0 divided by 1. So, that makes it 97 plus 1 is 98. So, that is where I get down this one, and then my 222 cross 222 is what is a straightforward calculation which I see over here. So, this is where you have both the spatial aspect as well as the temporal aspect being integrated together, and it comes down into one single output. Okay. So, if you look into this particular problem, what you can see is that with increase in this extra dimension over here, there is a significant increase in the total data overhead. Now, if you write down as in the earlier cases, we had been doing our pen and paper empirical solutions into what is the total parameter space, then we found out what is the model space in terms of bytes, what is the operational space requirement for the model, and what is the operational compute requirement for the model. Now, if we go down with the same logic over here and place down, because of this extra increment of dimension and this coming down to 98, now that is a huge burst up. So, it is almost 100 times more memory which it is going to take, and including these channel over here, these kernels over here are also going to get down one extra dimension of parameters which it has to learn. So, it is not just that the parameter space is exploding, it is also that you have an explosion around the operational space complexity. Now, this is an alarming factor. Because of these issues, it becomes really hard to actually operate on a substantially sized video. So, if my camera is acquiring something at 50 fps, so technically that means in 2 seconds of time I will have 100 frames acquired over there. Now, in 2 seconds of time, most likely my actions will not be changing significantly over there in any way, and if that is the situation, then I am not going to get down a substantial amount of description about the whole action in a video. Maybe I can just comment on 2 seconds what happened in these 2 seconds, but not what happened in the overall activity present over there. So, these are challenges which we would be facing while trying to do these analytics. And now, in order to get rid of this challenge, there is actually a very simple way which is called as spatio-temporal deep learning, and this is a rather effectively used way which a lot of people on the community work out on. Now, what it does is say I have my frames available over here on my video, then I am going to extract out all the frames over there, and now instead of considering like reorienting my dimensions on my video over here, what I choose to do is I choose to extract each frame and try to operate on each of them. Now, if I have this whole thing of t cross 3 cross m cross n, so what that would mean is I can pull out any one of these frame from here which is going to be of the size of 3 cross m cross n. Okay. So, let us pull out one of these frame. Now, what I can do is I have these ImageNet sized networks available to me for doing classification, and if I, as I had done in the earlier experiments, in most of our experiments what we had done is we took down a model which was more of solved for the ImageNet problem, and we were trying to solve something else. So, for a similar scale of data and to keep everything tractable, we were trying to solve it with the CFAR 10 problem over there, and for that purpose what we had done is we pulled out say VGGNet or GoogleNet or ResNet, DenseNet, any of these networks, and the image was taken down from CFAR and it was scaled up. So, while I was loading down a CFAR image, instead of a 32 cross 32, so I scaled it up to 224 cross 224 sized, and then I placed it into my network over here, and then I get down my total outputs coming. So, I was truncating my total number of classification layers over there. Instead of making it 1000 which is typically for ImageNet, I chop it off and make it just 10 decision layers. Now, if I am not adding this decision layer in any way, what I get down over there is just my feature vectors, and that is what I am going to consider over here as of now within spatio-temporal learning. So, the idea is that you pass it down through a network, and then if you keep down sending each individual frame in the same way, then you are going to get down an output tensor over here which has some k number of neurons. So, it is a k cross 1, that is just before the final layer for doing a fully connected network for classification. You have a linearized out, and then there may be some extra connections given down. So it depends on, you can have 4096 neurons over there, you can have 512 neurons, you can have 1024 neurons, any of these number of neurons. But then each tensor is what is corresponding to one frame. So technically this whole thing becomes a T cross K size tensor, where T is this dimension of the time length which goes down. Now if I come down from this video space over here, which has T cross 3 cross m cross n, now this whole thing is mapped down into a T cross K size tensor, where 3 cross m cross n dimension is what is mapped onto these K dimensions over here. So that's linearized and mapped and to a much reduced out space, whereas your time dimension still remains the same. And this is a concept which we are going to now make use of. So now that I have this K number of neurons, each representing one timestamp of a tensor, now I can use this as some sort of a timestamped feature which consolidates out my whole visual aspects on a frame, and then use it for passing through some sort of a sequence learning model. So this is basically a sequence of features which I have. So in the next lecture, what I am going to cover is something which is called as recurrent neural network. So I will introduce you the whole theory of a recurrent neural network, and then enter into something called as a long short term memory, which is one of the most viable ways of doing and solving out these recurrent neural networks. The input to this, which I would be calling as features or aspects or attributes over there, are what are these T cross K tensors, and each timestamp is one timestamp tensor which enters over there. So instead of keeping you waiting for long, so we will be doing those things tomorrow. So once we finish off in the next lecture the series and understanding and the theory behind what happens in a recurrent network for sequence modeling, in the subsequent one we are going to show you a clear cut example of how this problem has been solved out. So till then stay tuned, and thanks.